Hello. Here we'll talk about coordinate vector spaces and bases in general vector spaces. Again, let's start with fixing a ground field. Then the vector space of n coordinate vectors is the following. As I said, it is the Cartesian product of n copies of the ground field F. So that is the set of collections, or they are called vectors in this case, of numbers of elements from F. And the first statement is that this set is naturally a vector space over F. Two operations we need to define, which will make it a vector space. The first is addition, and on two vectors it gives the vector where we sum coordinates, this xn plus yn, component-wise, coordinate-wise. And the second operation is scaling, and again it's very familiar. So just scale, multiply with the constancy all the coordinates. So the little exercise is to check that these two operations fit nicely into the general definition of a vector space. These will be the model examples of vector spaces. These vector spaces will form a skeleton of the whole linear algebra. And we will also look at those vector spaces which might be defined differently, but in essence are coordinate vector spaces. So they will have to be isomorphic to one of those coordinate vector spaces. So let me just call it the coordinate vector space here. And the process of establishing an isomorphism between an abstract V and one of those is will be called coordinatization. And yeah, for an arbitrary given vector space, such process consists in giving an isomorphism from a coordinate vector space into V. And well, okay, suppose that we have such an isomorphism. What can we say about our vector space V? So let's look closely at the coordinate vector space. It is it comes naturally with a special collection of vectors. Let me from now on write my vectors as columns. That way they will take less space. So the special vectors I have in mind are those where the coordinates are as simple as possible. And in what sense simple? Well, simplest numbers are used as the coordinates. And the simplest of all the numbers is 0, and next simple is perhaps 1. So I will use as many zeros first as possible, and then, if necessary, we'll use ones. If I use all zeros, I'll end up with a zero vector, which is not interesting. So yeah, that is actually the part of the structure, but it's not really part of the structure. It's a consequence. If we multiply by 0, any vector will get the 0 vector. So all zeros is not so interesting. I will have to use 1 somewhere, and that's the result. So if I just put 1 in one place and zeros everywhere else, I'll have a very simply organized vector E2, that's what I'll call E1 if I place 1 in the first position, E2 for the second, and then all the way up to En. Well, this is just a plain game of constructing the simplest possible imaginable vectors, but these vectors actually have a very special property. Any vector I have in my vector space, so column vector x1 up to xn, I can write in a unique way as a sum of these vectors with some coefficients. So namely, I just take the first and multiply by the x1 coordinate, which in the vector x sits in this position. And I'll go all the way till the last, and the last vector in my collection here is multiplied by the last coordinate. So that is called the basis for just this property that any vector is uniquely, so for any vector I have unique numbers, always have them, and they are unique, expressing my vector as what is called a linear combination. And now if I have an isomorphism between my model vector space, the coordinate vector space Fn, and some other vector space V, I can use it to transform the special vectors, coordinate vectors, into some vectors in my vector space V. And this property will still be true. Isomorphisms are good for that, so all the properties which can be expressed in terms of linear algebra, they're still true. And what is the property now? It's that any vector in our vector space can be written in a unique way as a linear combination of this collection of vectors. So if we have the property, we call the collection of vectors a basis. And again, to be a basis, collection has to have two properties. Any vector is a linear combination and in a unique way. So now we could probably separate these two properties and reinterpret them in terms of these coordinatization maps. So this isomorphism, which is the same as to give a basis, I can call still a coordinatization or coordinatization map. So yeah, suppose that we, let's separate these two properties. Suppose that we are checking it in two steps. So the first would be that for any vector v, we have some coefficients such that v is equal to what does it mean in terms of the maps? First of all, we still have a map for any collection of vectors. Doesn't matter what the collection is, we can define a map like that just by saying that on the special vectors EI the values are VI's. Then this will be the so then for any vector x1 up to xn, the answer will be as if we just take this vector and apply phi to it and use the linearity of phi and pull the x's. I will write it in a compact way. Pull the x's, which are scalars, out of our map and end up with the values on EI. But that is the same as by this setting, that is the same as VI. So knowing these vectors, we know the linear map everywhere, just by linearity. That's where we use linearity. And if we have a collection of vectors v1 up to vn which has this property that any vector can be written as a linear combination, that is to say that our map, that is equivalent to saying that our map is surjective. That is a shortcut for saying that, so surjective. The second part, or we can also just do it from the set-theoretic point of view. Being bijective is being surjective and being injective at the same time. So we can just see, oh, what is the condition for this map to be injective? Again, this is the shortcut in representing that. Injective means that no two different elements go to the same. So if two elements go to the same, if two vectors in here go to the same answer, then they have to be the same. So we know what is for a vector go to one answer, and then a different vector will have to go to the same answer. What does it mean? The two linear combinations are equal. So for x's, some numbers called x's, we form a linear combination. And then for some numbers we call y's, we have another linear combination of the same chosen collection V. And they happen to be the same. So from there we have to deduce, we have to be able to say that all coefficients we used in here and in there are the same. So that is to be injective. But this equation we can rewrite in a different way. We can just take the difference of the two sides of the equation and combine the coefficients in front of vectors, and what we will have, so I'll call the differences xi minus yi, I will call them ci. So I will have alternative way of writing it. I will have this combination being 0, and that should imply that all differences, all ci's are 0. So this is called linear independence of vectors v1 up to vn, and this is called the spanning property. So that sometimes denoted like that. The span, the set of all linear combinations of vectors, is our v, and here we just say that vi's are linearly independent. So that is a special name for the property, which is equivalent to the map corresponding to the collection being injective. Well, run out of space, so that's it. See you later.